We saw already last time one way to define, which is not really a precise definition, but we saw, we roughly understood how to give this symbol here meaning. Okay, so we will say that the limit of f of x as x approaches a is equal to L if f of x is getting closer and closer to L as x is getting closer and closer to a. Now, maybe some of you have seen in high school already a more precise definition. This is not precise because normally if we define something in mathematics, we use symbols. And I have explained last time that using such a definition, there can arise some problems. In particular, if we have just such a definition, we have to rely on doing computations, using our calculator, doing computations, or plotting the graph of f of x in order to understand what will happen with the limit. Now, last time I also stressed that even though x is getting close to a, x will not be equal to a. We will stay away from a. This is something which is important in the definition of the limit. In most cases, or in many cases, not in most cases, the function will not even be defined at a. So for instance, you can consider this limit, even so if you just try to plug in 2 here, you see that the function is not defined, you get 0 over 0. Okay, but this is no problem for the definition of the limit. And if you do some computations, or maybe you use the method you have already learned in high school, you of course all know that the limit is 1 over 4. Now, if we change this function at a point 2, this will not have any effect on the limit, because this symbol, okay, once more requires that x is staying away from a. So, for instance, if you call this function f of x, and you define a function g of x which is different from f of x at a point 2, so for instance, you choose the usual definition if x is not equal to 2, and you choose anything, let's say 100 if x is equal to 2, the limit will be the same. So the limit of g of x as x tends to 2 will be the same as the limit of f of x as x approaches 2, even though the two functions are different at one point. But this point does not matter for the limiting definition because we stay away from a. Okay, so are there any questions to this? We saw last time some more complicated examples where we try to use the most simple approach, namely using the calculator, computing some values and trying to guess what is the limit, or plotting the graph. And last time in particular we saw the function f of x is equal to, or f of t is equal to the square root of 9 plus t squared minus 3 over t squared, where just relying on the calculator or plotting the graph by using Maple is not enough. We saw something strange will happen, and if you do not use any analysis based on computations, if you just rely on the computer or on the calculator, you will not be able to figure out what the limit here in this case is. This should also be one definition, one motivation why we will later on give a more precise definition of the limit. Now, before we do so, before we go on and give a more precise definition of the limit, we will discuss, just because at this stage everything is more easy, we do not have to consider details. So let's maybe at this stage also discuss shortly in which cases the limit does not exist. Now, a famous example is the so-called Heaviside function, which you find in our textbook. So this is a function which occurs normally in applications. So this function, denoted by h of x, is defined as 0 if x is smaller equal than 0, and 1 if x is larger than 0. So you can think about this function like switching on current. If you switch on current until if you consider x as the time, until time 0, current is switched off, so it's 0. Then you switch it on, so you go to 1. Now, in this case, of course, we can easily plot the graph. Okay, so this is the function where this is 1 here. And now if we try to figure out whether the limit of h of x as x approaches 0 exists or not, we see that we see already some basic idea. Namely, we see that if we come from the left, okay, if we approach from the left, the function is always equal to 0. But if we come from the right, the function is always equal to 1. Because of this, the limit cannot exist. Okay, so here from this we see already the limit does not exist. But this example here motivates the definition of so-called left-hand limit and right-hand limit. Because you see, in this case, how have we figured out that the limit does not exist? We consider just from the left and just from the right. Okay. Now, maybe you have already defined in high school left and right-hand limit just to fix the notation. For this specific example, we will write x approaches 0. This means here from the right. So x will always stay positive. So this is called the right-hand limit. And if we write a minus, then what we have is the left-hand limit. And you see from this example why this definition. So basically, if we see such a symbol, for now, we imagine, so this is equal to some number. If h of x approaches this number as x is getting closer and closer to 0 from the right, and here from the left. And this symbol is read as the limit of h of x as x approaches 0 from the right. That's the way this symbol is read in English. And we see that actually we have already some simple result which tells us that the limit of f of x as x approaches a is equal to L if and only if the limit of f of x as x approaches a from the right is equal to L, and the limit of f of x as x approaches a from the left is equal to L. And this already gives us a tool to figure out that certain limits do not exist. Okay, so for instance, in this case, we see that the right-hand limit is 1, the left-hand limit is 0, so they both exist but are not equal. So from this result, we can already conclude. Using such an argument, we can already conclude that the limit does not exist. So this is a quite handy tool in some cases in order to figure out whether a limit does not exist. Okay, so for instance, another example would be this function here, 1 over 1 minus 2 to the 1 over x. Okay, so maybe this function is a little bit more interesting. Here you see that if you approach 0 from the right, okay, because this is getting larger and larger, so this is getting larger and larger, what you get is 0. And if you approach from the left, okay, then you see that this is getting smaller and smaller, so this will tend to 0, so what you get is 1. It's not a proof, okay? Later on we will define also precisely those two notations. But as for now, we can use such an argument in order to figure out the limits. I guess you have seen this in high school, so there should be no question. Maybe just keep in mind the reason why we define such symbols is because this will provide a good tool in order to figure out that the limit does not exist. And later on, from the precise definition, we will see that to prove that the limit does not exist is not so easy just going back to the definition of the limit. Now there are, of course, apart from this situation where the function jumps, there are also other situations where the limit does not exist. Here's another easy example. So you look at the function f of x is equal to 1 over x squared. Now, if for this function you plot the graph, so the only way at the moment to figure out limits is we more or less rely on a picture. When we give the exact definition, one reason for giving a precise definition of the limit is to get rid of a picture. Now, if you plot the graph here, so you will have something like this here. Okay. Now you see if x is approaching 0, okay, no matter how you approach, the function is getting larger and larger, so the limit does not exist. But if you accept infinity as a number, okay, if you consider infinity as a number, you could say in some sense this limit exists here. And we say the limit is infinity. So you have the limit of f of x as x approaches 0. So we would like to write something like this. This does not mean that the limit exists in this case. This is just another instance where the limit does not exist. But the way the limit does not exist is very special, different to the previous situation where we have encountered where the function is jumping. So here, the function is getting larger and larger. It's another way how the limit does not exist. Okay, and similar you can then define, so similar, you can consider the limit of a function f of x as x approaches a is equal to minus infinity, or one-sided versions. Okay, and you know already from high school that this leads to the definition of asymptote of a function. So, x is equal to a is called vertical asymptote of, this is terminology, so vertical asymptote of f of x if one of the following limits relation holds. The limit of f of x as x approaches a is equal to either plus or minus infinity, or the limit of, as x approaches a from the right is either plus or minus infinity, or the limit of f of x, so here I have to write f of x, as x approaches a from the left is either plus or minus infinity. Okay, one of those. Okay, so either this one or 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 this one. 6 possibilities. In this case, the vertical line x is equal to a is called the asymptote, vertical asymptote of the function. So for instance, for this function, you have its x is equal to 0, so the y-axis is a vertical asymptote. And for instance, one of the functions we considered last time, the natural logarithm, has a vertical asymptote at x is equal to 0, because the limit of the natural logarithm as x approaches 0 from the right is equal to minus infinity. So you have one of those cases. There are also other examples which you find in our textbook, but you have learned this notation, I guess, in high school, so I'm not going to say more about this. So we have here seen 2 different, essentially different cases where limits do not exist. The first case was the function is jumping, and the second case was the function values are getting larger and larger. Now, of course, there are also other possibilities where the limit does not exist. We will have one example Namely, if you consider the following function, which is a famous example in mathematics, 0 if x is a rational number, and 1 if x is irrational. Now, this is another example which we will discuss in the homework assignments. Because maybe you have seen already our first homework paper, there are several problems related to limits. Now, you do not have to give a precise argument. At this stage, you can argue. Also for this function, you can just argue. You see here also that for this function is a little bit different from the previous ones. Namely, it's not so easy to plot the graph here. It's not possible to plot the graph. That's another reason why we have to give a precise definition of a limit, because we want to get rid of the picture. This is something which we always needed until now to figure out limits. Now, so this is one more motivation for giving a precise definition of a limit. Another one is if you want to prove something like this here. So for instance, you have some function a, and you know that the limit of f of x as x approaches a is equal to, let's say, L, and you have another function g, and you know that the limit of g of x as x approaches a is equal to, let's say, R. Okay, you want to prove or disprove that the limit of f of x plus g of x as x approaches a is equal to, of course, the obvious case is L plus R. Now, using our definition, so-called definition, we haven't given a precise definition yet. Of course, you would argue that, okay, this means that f of x is getting close to L, closer and closer to L as x is getting closer and closer to A, and this means that g of x is getting closer and closer to R as x is getting closer and closer to A, so the sum has to get closer and closer to the sum L plus R as x is getting closer and closer to A. Now, but you see already from this, this is not a mathematical method if you have to argue like this. We're not writing essays. Okay, so that's another reason why we want to give a definition of the limit just based on symbols. And this is the next thing which I want to do. I want to give a precise definition of the limit. And then I will come back to this example here. Actually, the only thing we have to do is we want to make precise what it means that f of x is getting closer and closer to L as x is getting closer and closer to A. Now, this will lead to the so-called epsilon delta definition. Okay, so maybe in this case, let's not start with the definition, but let's try to motivate it by looking at an example. So let's maybe look at the function f of x is equal to, now we can choose anything, so we choose 2x minus 3 if x is not equal to, say, 1, and we choose 5 if x is equal to 1. Okay, we know already that the limit of f of x, this is something we can figure out by computing some values as x approaches 1 is equal to minus 1. Okay. Now, as I said, this here means that f of x is getting closer and closer to minus 1 as x is getting closer and closer to 1. Okay. But this statement we can make precise. Namely, for instance, how close has x to be chosen to 1 if f of x, if the distance of f of x to minus 1 should be, let's say, smaller equal than 0.1. So we can quantify this. So this means, okay, we want to know, okay, how close do we have to choose x to 1 such that the distance between f of x and minus 1, its limit, is smaller or equal than 0.1. Now, of course, from this we can easily compute this. So we see that we just plug in f of x, so we get 2x minus 3 plus 1 minus 2. Okay, and we can write this as 2 times the distance between x and 1. And now we see, okay, if we make this distance here smaller or equal than 0.1 half, okay, so if the distance between x and 1 is smaller or equal than 0.1 half, okay, we will have achieved our goal. Namely, this distance here will be smaller or equal than 0.1. But of course, we have to stay away. So we have an end here. We have to stay away from 1. Otherwise, this is not true, okay, because of this exceptional value here. So you see from here, okay, actually, what I have said before, we can classify this, or we can make it precise. Namely, if you tell me 0.1, if you tell me the distance should be 0.1, I can tell you how close you have to go to x, to 1, how close x has to be to 1, such that you achieve this goal here. And now, the precise definition of the limit is that for every epsilon you tell me, I have to tell you a corresponding delta, such that if the distance between x and 1 is smaller or equal than delta, we will achieve our goal. Namely, f of x, the distance between f of x and minus 1 will be smaller or equal than epsilon. And this is the epsilon delta definition of the limit. Okay, so epsilon delta definition of the limit now the limit of f of x as x approaches a is equal to L. Okay, so this means, this symbol here means that for all epsilon larger than 0 you give me, there will exist a delta which might depend on epsilon, such that if the distance between x and a is larger than 0, we have to stay away from a, and smaller or equal than delta, then the distance between f of x and L is smaller or equal than epsilon. Okay. If you once more look at this example, you see that if I replace this here by epsilon, the same reasoning will be true if I replace this quantity here by epsilon half. And this epsilon half is our delta. Now, once more, this definition is just using symbols in order to make precise what I have said before, how I have defined this symbol before. Namely, once more, f of x should get closer and closer to minus 1 as x get closer and closer to 1. Okay? This just quantifies it. So for every epsilon, for every distance, you tell me you have to find the delta such that if you are so close to a, okay, the function values will be within an epsilon interval of L. And this will be our basis of the limit. From here we will start. Everything else we will deduce from this property. So whenever you are invited to prove such a relation by using the epsilon delta definition, you have to give me the delta. So whenever I tell you an epsilon, you have to give me the delta such that this relation holds here. And this is what you have to prove. Okay, so but maybe the difference to high school will be that for those who have learned this already, maybe the difference to high school will be that we systematically, from this definition, will start in order to deduce all our properties. And this is essentially what will happen today and what will happen next time and maybe also next week on Monday. Now, maybe it's good to look at the graph of the function f of x to understand the definition from the graph. So let's plot any function and maybe let's say this is our A here. Now from this graph we already see that as x is approaching A, our function value will approach L, which is this number here. Okay. Now what does this definition mean here? If you look at the graph, this definition means that whenever you give me an epsilon, which is something like this here, okay, where we have here epsilon, okay, whenever you give me such a strip, okay, of thickness 2 epsilon, I have to find the delta such that all the function values within this interval, okay, are mapped into the strip. So in this case, you see you have, of course you have several choices. You see, for instance, if you choose this here as delta, okay, then you see that now for all x which are within this interval here, okay, the interval from a minus delta to a plus delta, so this interval here, all those x, the corresponding function values are within the epsilon strip. Okay. So for instance, this delta here, for this epsilon, this delta here will do the job, will work. Okay. But you can choose, of course, any smaller delta. It's also okay. Okay. Once you have found the delta, you can choose any smaller delta, and this will also satisfy this definition. Now, you can imagine, I just showed an example where this was easy to find the delta. But if I give you a more complicated function, this might not be that easy. You find in our textbook an example, this function. So f of x is equal to x to the cube minus 5x plus 6. Okay. And we are interested in the limit of f of x as x approaches 1, which is equal to 2. Now, for instance, if I give you the epsilon 0.2, okay, then you have to find a delta such that for all x in the delta interval around 1 here, you get that the absolute value of x to the cube minus 5x plus 6, so our function, minus 2, minus the claimed limit, so this is what we want to prove, minus the claimed limit is smaller or equal than 0.2, okay, whenever x, the distance between x and 1 here is smaller than 0 and smaller or equal than the delta which you have to find. Okay. Now you see, already from this example, it's not so easy, okay, because something like this, it's not so easy to figure out, okay, how close does x have to be to 1 here. Of course, you can plug this into Maple. You can use Maple to plot this graph here. And then you can try to, just by looking at the graph, okay, you can try to figure out, as I have done here, what is the corresponding delta. Okay? But this is not enough to prove this relation, because this is just one specific choice of epsilon. But you have for all epsilon, you have to give me a delta. Okay? So you see, for this example, even for such a simple function, it's not so easy. And we will later on understand how we are still able to do it, not by doing it directly, but using another approach. This is something what you essentially have done in high school. Maybe let's spend some time, let's look at some simple examples in order to figure out how to use this definition here directly. So maybe let's start with a very easy example. Now you see that normally if you want to prove the limit, the first thing you need a guess. Okay. In this case, it's easy to make a guess because you know already from high school. Also, it's easy to plot the function and look just at the graph of the function and get a guess. So the guess is that the limit will be equal to 1. Now it's the first step to get a guess. So you think that something like this is true. And the second step is to use the definition to prove it. Okay. Now what we want to do is, okay, so we have to look, the epsilon is given. So you have to look at the distance between f of x and the claimed limit 1. Okay, but in this case, again, it's easy. You just plug in the function. So you get 3 times x minus 1. Okay, and you want to have this smaller equal than epsilon. Now you look at this here, and you see, okay, from here, you see that delta must be equal to epsilon over 3. Okay, so this is you don't have to write this in the homework paper. Okay, this is you try, okay, to find the right delta. And now what you write in your homework paper is you just write down precisely how to prove it. Okay, so let epsilon be larger than 0. Choose delta to be equal to epsilon over 3. Then whenever x, the distance between x and 1 is larger than 0 and smaller equal than this delta here, we have that the distance of f of x minus the claimed limit is equal to, you plug in, so 3x minus 3 is equal to 3 times x minus 1. And because of this relation, you have a smaller equal than 3 delta. But because of the choose of delta, you see this is equal to epsilon, and you are done. So this is what you write down. This is the proof. Okay. So if I ask you to prove something like this here, what you write down is this here. Okay. This is just this. You can say our textbook is using 2 steps. The first step is this one, trying. Okay. Trying to find the right delta. The second step is this one, which is proving it precisely. Okay, so, but this example is quite easy, so maybe let's look at something which is a little bit more challenging. Now, what is more challenging? Slightly more challenging is to look at this function here. Okay, so you know that already from high school, but now we are going to prove it. You know that this limit, for instance, is 4. Okay. Now, how to use the epsilon delta definition to prove this? So again, you have given an epsilon, you have to find the delta. So you have to make sure that the distance between f of x and the claimed limit, okay, is smaller equal than epsilon. This is what we want to have. Now you see, okay, you can again you plug in the function. You have x squared minus 4, and the obvious way to do this is to use the well-known formula that this is x minus 2 times x plus 2. Okay, so you see that this is the absolute value of x minus 2 times the absolute value of x plus 2. Now this is causing a little bit problems here, okay? Because you know that if you choose a delta, okay, you will have that this is smaller equal than delta, but you have still this term here, okay? So, but you can, because x is getting close to 2, okay? So you can assume that the distance of x to 2 is small. Let's say smaller equal than 1. Okay? So assume the distance between x and 2. Okay, so from this you get that x is larger equal than 1, smaller equal than 3. Now, if you assume this here, you see that this is no problem. This will get smaller equal than 5. So you have that this is smaller equal than 5 times the distance between x and 2. And now you see that how to choose the delta, namely epsilon over 5. Okay. So now choose delta to be equal to epsilon over 5. If you plug this in here, then you see that this is then smaller equal than epsilon. Okay. So this means here, this means that the distance between x and 2 has to be larger than 0 and smaller equal than epsilon 5. But now for this distance, we have 2 conditions, this and this one. And you have to make sure that both conditions are satisfied. So you just have to assume that the distance is smaller equal than the minimum of those 2 here. Okay? So call this delta 0. So our right delta will be the minimum of delta 0 and 1. Okay, now we have found it. And now we can write it down as a proof. Okay, so we notice that this here is the right delta. So I will write out the complete proof once more. You can consider the step, what I have done till now, as trying around to find the right delta. And now the proof follows. Epsilon be larger than 0. Choose delta to be equal to the minimum of epsilon over 5 and 1. Now, assume that the distance between x and 2 is larger than 0, smaller or equal than delta. From this you get that the distance between x and 2 is larger than 0 and smaller or equal than both epsilon 5 and one. Then you get, if you look at the distance between f of x and your claimed limit, which is 4, and you plug everything in, so you have x squared minus 4. You can write this as x minus 2 times x plus 2. You can use this here as before to bound this by 3, and this will be bounded by 5, and this will be bounded by epsilon over 5. So you get smaller equal than epsilon over 5 times 5, which is equal to epsilon, and you are done. This is what you have to write down in your homework paper. What I have done before is trying around to find the right delta. You see here it's a little bit more tricky because the function is more complicated, so it's getting a little bit more tricky. Okay, but now we are also able to deduce some basic facts about limits. Now we will do some more examples just that you get used to this, because if this is new for you, then you are not used to it yet. And we will do more examples than in the homework assignments. Now, you will say that, okay, now every time if I encounter a limit, every time to prove something like this here, for every epsilon to give the delta is a complicated procedure. Now, what we want to do in the sequel is to simplify this procedure, to make it more easy. And in order to simplify it, we will prove some basic facts about limits. Now, one of those basic facts I told you before, so if the limit of f of x as x approaches a is equal to L, and the limit of some other function g of x as x approaches a is equal to R, okay, we want to prove that the limit of f of x as x approaches a, f of x plus g of x, will be equal to the sum of the limits. Okay. If we have established something like this, then we know, for instance, already that the limit as x tends to 2. Now I didn't choose the examples very well, sorry. So x squared plus something which we can handle simula as before. So if you have as before, you can for this we have proved that this is equal to 4. For this here, as before, using the same method, you can prove that this is equal to 2 here. And now for this new function here, the sum of the two functions, you do not have to use the definition once more. You just apply this here. Okay? And you see that this will be then equal to the limit as x tends to 2 of x squared plus the limit of 2x minus 2 as x tends to 2, which is equal to 4 plus 2, so 6. Okay, so you see here already why we want to prove something like this. Once we have figured out something like this, the task of proving that some limit relation holds getting easier, because we have already, if we have proved it already, the limit relation for quite a lot of functions, now we can add, okay? We can, like this, get even more examples. And we do not have to go back every time to the basic definition of the limit. This is what we want to do maybe next time. So next time I will show you quite a lot of such basic laws, and then we just combine from simple limits. So we will prove that such a relation holds by using the epsilon delta definition for some simple limits, and then we will use such construction rules to construct more complicated functions, and thus be able to prove limit relations without every time going back to the epsilon delta definition. Now, for such a law, we have to go back to the epsilon delta definition and prove it once and for all, and then we can accept this as one of the basic laws. So let's try to use here this definition here. Okay, so again, given the epsilon, we have to find the delta such that the distance between f of x plus g of x minus the claimed limit, this one, will be smaller or equal than epsilon. We have to find the delta. Now you see, of course, because we know already that those two limit relation holds, so it makes sense to write this, to decompose this as f of x minus L plus g of x minus r, and then use the triangle inequality. So this is smaller or equal than the difference between f of x and L plus the difference of g of x and r. Okay. Why is this helpful? Because we know already that those two relations are established. So we know that for epsilon, we can find a delta such that if x is close to a within a delta distance, the difference between f of x and L will be smaller or equal than epsilon. And the same for here. So this will, if we choose x small enough, this will be smaller or equal than epsilon, and this will be smaller or equal than epsilon as well. So everything will be smaller or equal than 2 epsilon. So if we start here with epsilon half and here with epsilon half, we will get smaller or equal than epsilon. Okay? So what we need now is, okay, so if we look at epsilon half, okay, there will exist a delta 1 such that if the distance between x and a is smaller or equal than delta 1, then the distance between f of x and L will be smaller or equal than epsilon half. And because of the same reason, there will exist a delta 2 such that if the distance between x and a is larger or equal than 0 and smaller or equal than delta 2, then the distance between f of x, g of x and r will be smaller or equal than epsilon half as well. And now we choose as delta the minimum of those two. Because if we choose the minimum of those two, both relations will be satisfied. This will be smaller or equal than epsilon half, and this will be smaller or equal than epsilon half, and overall we will get epsilon. Okay? So for the epsilon, we will choose the delta to be equal to the minimum of those two, delta 1 and delta 2. And those two have to exist because we know already that this relation is satisfied. You still can follow. So I write out the whole proof. Because this was, again, first step, guessing the delta. Okay, so once more, I spend time to write out the whole proof. Okay, so again, we start with an epsilon larger than 0. Okay, then choose delta 1 and delta 2 such that the following relations are satisfied. If the distance between x and a is larger than 0 and smaller or equal than delta 1, then the distance between f of x and L will be smaller or equal than epsilon half, and if the distance between x and a is larger than 0 and smaller or equal than delta 2, then the distance between f of x and r will be smaller or equal than epsilon. This is possible. Choosing such constants is possible because those two limit relations are already satisfied. We know already that this limit relation and this limit relation holds, and we just apply the definition. Okay. Now choose. Now let delta be equal to the minimum, the smaller one of delta 1 and delta 2. Okay. Assume that the distance between x and a is larger than 0 and smaller or equal than this delta. Then from this relation, you will get that the distance between x and a is smaller or equal than delta 1, of course larger than 0, and the distance between x and a is smaller or equal than 0 and smaller or equal than delta 2 as well. So both will hold. Now, because both will hold, you will have this and this here. So now, if you look at the distance between the sum f of x plus g of x minus L plus R, okay, you can use again triangle inequality. So this will be smaller or equal than the distance between f of x and L plus the distance of g of x and R. And now you can use this here. So this will be smaller or equal than epsilon half, and this as well. So this is smaller or equal than epsilon half plus epsilon half, which is equal to epsilon. This finishes the proof. Because now I have, for any choice of epsilon, I have told you how to choose the delta such that if we are close enough to A within the delta interval, the f of x plus g of x will be close enough. Smaller, it will be within the epsilon interval of the claimed limit. And this proves the limit relation. Okay, so are there any questions so far? Now, this is not the only limit. We saw before also there are other limit relations like left-hand limit, right-hand limit, and infinite limits. Now, of course, you can give the same epsilon delta definition also for the other limits. Okay, I just, maybe I erase everything, or you still need this? I will erase slowly, then you can also, for those who have already written this down, they can think about questions, whether they have questions. I haven't heard any question today. Now, as I said, also for the other limits I have introduced at the beginning of the lecture, we can give now a similar definition. So, for instance, if we consider the right-hand limit, so the limit of f of x as x approaches a from the right, this is equal to L. Now, what does this mean? Again, for all epsilon larger than 0, okay, there has to exist the delta, which might depend on epsilon, okay, which can depend on epsilon, such that if we are close enough, if we are within a delta, 2 delta, an interval of length 2 delta of x, f of x will be close to L. This was our original definition. Now the only difference is that if x is larger than a and smaller than a plus delta, we just care about one side. Okay, then the difference of f of x and L will be smaller or equal than epsilon. So the only difference is here. We just stay away. Of course, we stay away from A, and we are just on the right. Now, if you similar definition for the left-hand limit, and a similar definition, so similar for the limit f of x as x approaches A from the left, and also a similar, slightly not really similar, a little bit different definition for infinite limits. Okay, so what does this symbol here once more mean? This means that f of x is getting larger and larger as x is getting close to A. So here for every large pound, for m large, okay, you have to give me a delta which might depend on m, such that if the distance between x and A is smaller equal than our delta, then f of x is large. Okay, then f of x will be larger than m. Okay, and this for every large m. So here it's a little bit different. Here the important case here is if the case where epsilon is getting smaller and smaller, okay? Smaller and smaller, because we want to make this distance here as small as possible. But here, the important cases are large m, okay? So again, if we look at the graph, so maybe let's stick to the same example. We saw already that the limit of 1 over x squared is x tends to 0 is equal to infinity. So in this case, where is my color chalk? The graph looks like this here. Now, if you want to prove such a limit relation, okay, you have to tell me the delta for every m. So if I give you a large m, okay, you have to give me an interval around 0 such that all function values are mapped above this bound m. So you see here, again, you have several choices. The best choice will be this one. Okay, so if you choose, it doesn't matter whether I write here larger or larger equal. So if I have larger equal, then you can choose this delta here. And this delta will do the job. Okay, because for all those x here, the function value will be below n. Now again, maybe let's look at a very easy example. Maybe let's prove this here precisely by using this definition here. So we want to prove now this relation. Okay, so given is a m, and you have to give me a delta such that this distance that the function is larger than m. Now, you see this is quite easy here because you choose x to be smaller than 1 over square root of m. Actually, you have an absolute value. Okay, because if you just take the inverse, then x squared has to be smaller than 1 over n, and then you take the root on both sides. You will get square root of x is smaller than 1 over the square root of m, and this here will serve as our delta. Okay, so in this case, it's very easy. So, but again, this actually what I do here is I guess the delta, and now I can write everything down precisely. So let m be larger than 0. Choose delta to be equal to 1 over the square root of m. Now, if the distance between x and 0, so this here is larger than 0 and smaller or equal than delta, then doing the same in reverse, because this is if and only if, we'll get that 1 over x squared, which is our function f of x, is larger than m, and we are done here. Okay, so this is once more the first step, guessing the right delta, and this corresponds to the second step, writing down the proof. And this is essentially what you have to do in your homework paper. You do not have to show me this part here. Okay, just this here. Now, maybe it's interesting to discuss, okay, starting from the definition, how to see from the definition that the limit does not exist. What does it mean that the limit does not exist in this precise context? So for this, we go once more back to the definition of the limit. Okay, so maybe let's go back to one example, to our most simple example where the limit does not exist, namely the Heaviside function. So we have 0 if x is smaller or equal than 0, and 1 if x is larger than 0. And we saw already that the limit here in this case, intuitively we saw already that the limit does not exist. But maybe it's worth it to study one example to see how does this relate to the definition. Okay, so once more. maybe let's once more write down the definition. So the limit of f of x as x tends to a is equal to L. This means that for all epsilon larger than 0, there exists a delta which might depend on epsilon, such that if the distance between x and a is larger than 0 and smaller equal than delta, then the distance between f of x and L will be smaller equal than epsilon. Okay? Now you want to prove that the limit does not exist. Actually, this is more complicated in some sense than proving that the limit exists. Because if you want to prove that the limit does not exist, you have to show that for all L, this specific L is not the limit. Okay? This is already one problem. Okay? You have to do it for all L. You have to show that for every number, okay, no matter how you choose the number, okay, this will not be the limit. Okay? So you have to choose that for all L, there exists a delta such that for all delta, no matter how small you choose, for all L, there exists the epsilon such that for all delta, okay, you can find the x such that the distance between x and a is smaller equal than delta, but f of x, the distance between f of x and L, will be larger equal than epsilon. Okay, so this is quite different. You have to say this independent from the definition, you have to prove that no matter for which L, okay, no matter how small you make the delta, okay, there are still some x such that f of x will be mapped outside the epsilon interval. Okay, no matter how you choose the epsilon. Okay, so maybe for this case, how are we going to prove? Look, just looking at the definition, okay, why is the limit of h of x as x tends to 0 not equal to 1? Okay, why is this not satisfied? Okay. Now you see, so here you see, normally if you negate something like this, okay, logically, for all will become there exist and so on. So now what you have to show is, if you want to prove that this does not hold, okay, you have to give me one epsilon, okay, such that no matter how small you make delta, there are always x which are mapped outside the epsilon strip. Okay, one such epsilon which violates this condition is enough. Okay. Now, in this case, maybe some of you can easily guess what is the epsilon. What is the epsilon such that no matter how small I make the delta interval, I will always have function x such that the function value is outside the epsilon strip. You see here, if you choose 1/2, epsilon is equal to 1/2. No, unfortunately, I don't have any other chalk, so I have to use this here. So if you choose 1/2, okay, then you have this epsilon strip here. Okay. Now, no matter how small you make delta, you will always find x, namely negative x, which are mapped outside the epsilon strip. Okay. So this epsilon here, epsilon is equal to 1/2, tells you that something like this cannot be satisfied for all epsilon. And like this, you have proved that the limit is not equal to 1. Now, how do you prove that the limit is not equal to 0? You choose the same epsilon, 1/2. Then the strip moves down here. Okay. How do you prove that the limit is not any other number? For instance, how do you prove how do you prove that this is not the limit? And L is equal to 1/2. So let's maybe make this more specific. Again, it's enough to find one epsilon. So this is different. If you want to prove that such a limit relation holds, for all epsilon you have to tell me the delta. If you want to disprove, if you want to prove that such a relation does not hold, it's enough to give me one epsilon such that for all delta, this does not hold. Okay? So in this case, you see, you can choose, for instance, this epsilon strip here. Okay? For instance, you can choose epsilon to be equal to 1 over 4. Okay? Then, no matter how small you make delta, okay, the function, for all x, the function value will be outside the epsilon strip. So this cannot be the limit. That's the way you have to argue by using the epsilon delta definition of the limit. So this does not hold because if you choose epsilon to be equal to 1 over 4, then for all delta and x with the distance between x and 0 is smaller or equal than delta, we have that the distance between f of x and 1/2 will be larger than 1 over 4. Okay, so this epsilon here will violate this definition because for this epsilon you cannot find the delta. This is the main thing. Now maybe already from here you see that mathematics, how we are going to do it here at the university will be quite different from high school. We have to make things more precise. Now, but as I told you later on, maybe today and next time we will prove some basic laws, and then we will just use those basic laws in order to figure out limits of more complicated functions. The more you know, the easier it gets, because you can just, if you have a new example, you can try to relate it to an old one by using the laws and using what you already know. That's why the next step is to prove limit laws. One of them we saw already, namely the limit of a sum is equal to the sum of the limits. This is what we proved before. Now, there are a couple of other laws. So this is now in our textbook, corresponds to section 2.3, which is called calculating limits by limit laws. Okay, and actually this section starts with a theorem which collects already quite a lot of limit laws. So maybe I will just copy this on the blackboard. So assume that the limit of some function f of x as x tends to a and the limit of f of x of g of x as x tends to a exists. This is an example. This is an assumption which you need. Now you have a couple of laws. The first law is that the limit of the sum, as we have seen already, as x tends to a, will be equal to the sum of the limit. So the limit of f of x as x approaches a plus the limit of g of x as x approaches a. We have proved this already by using the epsilon delta definition. Now, of course, if you have here a minus, then you will have here a minus. Okay. Then another law is that the limit of a product is equal to the product of the limits. You can try to use the epsilon delta definition to prove something like this. It's not complicated, but a little bit more complicated in this case. Now, you have something similar for a quotient. But of course, you have to ensure that this limit is not 0. Otherwise, this cannot hold. It's not equal to 0. Okay. You have another simple one, which I forgot, namely the limit c times f of x as x approaches a is equal to c times the limit f of x as x approaches a. Okay, and you have some simple relations like the limit of a constant as x approaches a is just a constant, and the limit of x as x approaches a will be equal to a. Okay, so this is some base for some functions, and these are some laws to how you can build from some simple examples. Of course, for all those limit laws, okay, you have to use the epsilon delta definition to prove it. For some cases, it's very simple. Here, it's very simple because the difference between c and c is 0. So you can for delta you can choose anything, and you will certainly your f of x will be certainly close to c. Now, also here, it's very simple to find the delta. For this case, we have done it already, and for the other cases, you can try it. This is one method, or you can look at the back of our book where you can find the proofs. But if you want to make sure that you understand the epsilon delta definition of the limit, it's better to try it. Okay, to try for one of those. Of course, this is slightly more complicated than this case, and to prove this here by using the epsilon delta definition is more complicated than this one. Okay, it's getting more and more complicated, but it's not really complicated. I'm not going to do this in this lecture. And this is the last thing I want to do is I will just show you that this is already very helpful. Okay, because just once you have proved these basic laws, you can already prove that if p of x is a polynomial, you all know what a polynomial is. I write it down, then you know it. an x to the n plus an minus 1 x to the n minus 1 plus and so on plus a constant. So this is called polynomial. Okay. Now, for such a polynomial, just following from those laws, okay, you already know this. Why do you know this? From this one, okay, this limit law and this one, okay, you can deduce that the limit of x squared as x tends to a, if you apply this one, is equal to a squared. And then you go on like this, so you can prove that the limit of x to the n as x tends to a is equal to a to the n. You just need this one and this one to deduce this. Okay, and then you have already this term here. The constant you get by this one, okay, and then you use this rule to add up. And you see this is useful to do it like this because we have seen before an example of a cubic function x to the cube where it would not be easy for every epsilon to give me the delta, okay, directly. So you see from here already that it makes sense first to figure out limit relations for some simple functions, then to observe some building rules, okay, how the simple operations preserve limits, and then use this to prove something like this, because now we know already for every polynomial function the limit is, you just get it by directly plugging in the value a. Okay, but maybe at this point once more, I want to emphasize once more, this relation tells you that you have to keep away from a. Okay, but this just tells you that in this situation it's very easy to compute the limit, namely you just can plug in, and that's it. If you have a fraction of polynomials, such a function is called the rational function Yoli Hanshu. Okay, if you have a fraction of polynomials, you see, if you now apply this one, if the denominator is not equal to 0, you get already the same result for a fraction, for every rational function where a is not a root of the denominator. And this you get everything from those rules. Okay, so now, at this stage, we do not have to go back to the epsilon delta definition of the limit. Okay, are there any questions? No questions today. Maybe next time.